Trying to grasp the scale of the universe, with its stars, planets, and galaxies, using our familiar earthly perspective, is as futile as attempting to understand the entire ocean from a single droplet. You might perceive a comet gliding across the cosmos with its tail of ice and dust as a minor celestial event, but its true dimensions can easily dwarf the metropolitan areas we call home. Likewise, galaxies, with their glowing, spiral limbs composed of countless stars, are so immense that light itself requires tens of thousands of years to journey from one side to the other. I invite you on a voyage across the limitless stretches of the cosmos, heading directly for the heart of our home galaxy, the Milky Way. In this realm, conventional measurements like miles and kilometers become meaningless. Instead, we gauge distances in light years. Here, the standards for size are no longer based on our world, but are expressed in proportions that include entire star systems, galactic clusters, and galaxies themselves. To begin, let's try to conceptualize the sheer scale of the cosmos, starting right here with our home planet. Imagine for a moment that you could reduce the Earth to a minuscule point on a page. In this scenario, our moon would be a nearly undetectable fleck just a few centimeters from it. On this same scale, the sun would transform into a sphere the size of an orange, situated roughly 5 meters away from our microscopic planet. As you venture beyond our solar system, you discover that the stars we see as faint, shimmering dots are often monumental in size. For instance, UY Scuti, a red supergiant in the Scutum constellation, would be comparable to a balloon expansive enough to fill a grand auditorium if our sun were the size of that orange. I want you to hold that image in your mind, the contrast between a simple orange and an enormous balloon. As you venture beyond our solar system, you discover that the stars we see as faint, shimmering dots are often monumental in size. For instance, UY Scuti, a red supergiant in the Scutum constellation, would be comparable to a balloon expansive enough to fill a grand auditorium if our sun were the size of that orange. I want you to hold that image in your mind, the contrast between a simple orange and an enormous balloon. Our solar system resides within the galaxy known as the Milky Way. When you look up at the night sky, you see this immense collection of stars as a radiant stripe, where billions of suns are clustered so tightly they seem to blend into a unified glow. This illusion is created by our vantage point from within the galactic disk, as we observe it from an edge-on perspective. The name itself, Milky Way, comes from the Latin term Via Lactea, which is a direct translation of the ancient Greek Galaxias Kyklos, or Milky Circle. According to ancient Greek lore, this name originated when Zeus placed the baby Heracles at the breast of the sleeping goddess Hera, hoping the infant would gain immortality from her divine milk. When Hera suddenly awoke, she forcefully rejected the unfamiliar child, and the resulting spray of milk scattered across the heavens, forming the starry path we see today. This mythological origin perfectly captures the galaxy's visual character, which resembles a spill of milk or a luminous trail of cosmic dust. Shifting our focus to the sheer magnitude of our galaxy, you should picture the Milky Way as an enormous vortex of stars that extends for thousands of light years in every direction. At the very heart of this stellar maelstrom is a supermassive black hole named Sagittarius A star, which packs the mass of 4 million suns. On a scale where our planet is just a tiny dot, this black hole would be the size of a small marble, yet possess enough gravitational force to ensnare anything that ventures too close. Now, if you were to imagine Earth as a point just 1 millimeter across, the Milky Way's diameter would be about 6 times the real-world distance separating our planet from the Moon. A comparison worth pausing to consider. When you extend your view beyond our own galaxy, you find that our closest galactic neighbors, like Andromeda, are millions of light-years away. The distances involved are so staggering that astronomers switch from kilometers or even light-years to a unit called the megaparsec, where a single parsec is equivalent to approximately 3.26 light-years. The term parsec itself is a blend of the words parallax and second, reflecting its astronomical origin. It's a particularly useful unit because it enables scientists to calculate stellar distances using Earth's own orbit as a measuring baseline, without ever leaving our solar system. To put it simply, if you were to view one astronomical unit, the distance between the Earth and the Sun, and it appeared to span an angle of just 1 arcsecond, you would be looking at an object that is precisely 1 parsec away. Our universe is populated by billions of individual galaxies, and each of those galaxies is home to billions of its own stars. The portion of the cosmos that we can actually detect is a sphere with a radius of about 46.5 billion light-years, giving it a total diameter of nearly 93 billion light-years. A figure of this magnitude is so enormous that it completely transcends our normal understanding of size and distance. Trying to represent this scale with everyday analogies is almost impossible. Even if you were to shrink the Earth to a millimeter-sized dot, the observable universe would remain far too large for any earthly comparison to be meaningful. On such a cosmic scale, the most massive objects we know, our planets, mountains, and continents, would become utterly insignificant, highlighting just how much smaller our planet must be imagined than even a single dot on a page. Here is a final comparison to truly grasp this immensity. If you were to shrink the Earth down to the size of a single hydrogen atom, our Milky Way galaxy would, on that same scale, have a radius comparable to that of the actual planet Earth. Take a moment to consider that relationship, an atom to a planet. This analogy reveals the true proportion of our world to our galaxy. And with this perspective in mind, we can proceed. The core of our Milky Way galaxy remains a subject of intense scientific curiosity, shrouded in profound cosmic enigmas. It is concealed from our direct view by thick veils of interstellar dust and gas, which effectively block and disperse visible light. Nevertheless, scientists are able to pierce through this obscurity by observing the galactic center with radio, infrared, X-ray, and gamma-ray telescopes, revealing its secrets. The most prominent object discovered at the heart of our galaxy is the supermassive black hole, designated Sagittarius A star. You might hear astronomers refer to it by different names, but in English, it's known as Sagittarius A star. This object is a black hole, a celestial body with a gravitational pull so immense that once something crosses its event horizon, nothing, not even light itself, can escape. Our galaxy's central supermassive black hole possesses a mass 4 million times greater than our Sun. And it is this incredible object that controls the movement of stars and gas clouds throughout the galactic core. A variety of celestial objects are trapped in orbit around this black hole, including distorted gas clouds, which researchers suspect are the remnants of stars torn apart by the tidal forces of Sagittarius A star. The name itself, Sagittarius A star, refers to the compact and powerful source of radio waves found at the very heart of our Milky Way galaxy. The first part of its designation comes from its location in the sky, as it appears in the direction of the constellation Sagittarius. The Sagittarius constellation is particularly significant because the very plane of our galaxy cuts through it, revealing a rich tapestry of nebulae and star clusters. If you picture the Milky Way as a flat disk with a central swelling, you will have a good idea of its structure. This central part, known as the galactic bulge, is a dense collection of stars that typically envelops a supermassive black hole, while the flat, disk-like section is where you'll find the spiral arms, composed mostly of gas and dust. Our own solar system resides within this flat, disk-like region, positioned roughly 2/3 of the distance out from the galactic center, and nearly level with its main plane. Because of this vantage point, whenever you gaze toward the galactic equator on a clear night, your view is filled with the countless stars, dense dust, and sprawling gas clouds that make up our galactic disk. The letter A in the name signifies that it is among the most brilliant sources of radio waves in its celestial neighborhood, a common practice in astronomy where letters often denote brightness or discovery sequence. The asterisk, however, serves a special purpose. It highlights the object's compact nature and profound importance. It tells you we're observing not merely a bright spot, but an incredibly dense and massive body, the supermassive black hole at our galaxy's core. In essence, the name perfectly describes a compact, radio-emitting black hole in the Sagittarius constellation, a feature vital to our understanding of the Milky Way's structure and behavior. If you want to find the constellation Sagittarius for yourself, timing is key. For observers in the northern hemisphere, the best viewing months are from June through September, while those in the southern hemisphere should look for it during their winter. You will need to find a location far from the glare of city lights once the constellation has climbed high above the horizon after dusk. Sagittarius is situated in the most crowded, star-filled section of the Milky Way, so if you can spot the hazy band of our galaxy stretching across the sky, you are already looking in the right area. To pinpoint its exact location, you can use the nearby constellation of Scorpius as a guide. Its bright stars and unmistakable stinger-like curve make it easy to spot. Sagittarius lies just to the east of Scorpius, and if you need more assistance, remember that you can always turn to astronomical charts or smartphone apps, which provide real-time maps of the night sky to help you navigate the cosmos. The galactic center holds other fascinating features, most notably the galactic bulge. This is a dense concentration of stars, gas, and dust that swells out from the center, both above and below the main galactic disk. This central area is also home to a high density of exotic phenomena, from neutron stars to other black holes. For instance, the intense gamma rays detected from the galactic center might be a sign of activity near the supermassive black hole's event horizon, or perhaps even the annihilation of theoretical dark matter particles. So, what stops the entire galaxy from being pulled into this central supermassive black hole? A few critical factors are at play. The primary reason is that stars orbiting the galactic center generate a centrifugal force, which pushes outward and directly opposes the black hole's immense gravitational pull. You can think of it in the same way the Earth orbits the Sun. Our planet's forward motion prevents it from simply falling into the star. Additionally, the black hole is not the only source of gravity. The galaxy's total gravitational field is a combination of everything within it, all the stars, planets, gas, and dust. Crucially, a huge portion of this mass is attributed to dark matter, which creates its own vast gravitational field that helps stabilize the entire structure against collapse. The galaxy exists in a state of dynamic equilibrium, where gravity's inward pull is perfectly offset by the outward forces from the motion of stars and gas. The angular momentum of these stars and gas clouds is another vital part of this equation. To help you visualize what I mean by angular momentum, I will use a simple example that anyone can grasp. Picture a spinning top on a table. That top possesses angular momentum, which is essentially a measure of its rotational energy. This value is determined by both the top's mass and its speed of rotation. A fast-spinning top is difficult to knock over, signifying high angular momentum, whereas a slowly spinning one is easy to stop, indicating it has much less. Consider the Earth's orbit around the Sun as analogous to a spinning top. Earth maintains its continuous journey around the Sun because of a property known as angular momentum. If you picture a top spinning in a perfect vacuum, untouched and unaffected by friction or gravity, it would never stop. In precisely the same way, our planet continues its orbit indefinitely because angular momentum is a conserved quantity in the universe. This principle extends to all objects throughout the galaxy. Much like a top spins until an external influence halts it, celestial bodies maintain their rotation until acted upon by an outside force. For matter to be drawn into a black hole, it first has to shed a vast amount of its angular momentum. This process requires time and typically happens through dynamic interactions with the emission of radiation, preventing even the most massive black holes from instantly consuming their surroundings. While the black holes at the centers of galaxies possess immense mass, this mass represents only a tiny percentage of the galaxy's total. For instance, the black hole at the heart of our Milky Way, designated Sagittarius A star, has a mass equivalent to about 4 million suns. However, the mass of our entire galaxy is estimated to be in the trillions of solar masses, dwarfing the central black hole's contribution. The rotation of a galaxy is not driven solely by the gravitational pull of its central black hole. The true dynamics of galactic spin are dictated by the distribution of all its mass, which includes dark matter, stars, planets, and interstellar gas and dust. While the central black hole adds to the overall gravitational potential, the combined mass spread throughout the galaxy exerts a far more significant influence on its motion. Dark matter, believed to constitute a major portion of a galaxy's mass, is instrumental in generating the gravitational field that binds the galaxy together and defines its rotation curve. This curve reveals that the outer parts of galaxies rotate at surprisingly high velocities, speeds that are inconsistent with what we would expect if all the mass were concentrated in the center. The observed speeds are a key piece of evidence pointing to the existence of this unseen matter. If it turned out that dark matter did not exist, our current understanding of cosmology would require a complete and radical overhaul. In a universe without it, astrophysicists would face the challenge of finding new explanations for numerous astronomical phenomena now attributed to dark matter's influence. One such alternative is a theory called modified Newtonian dynamics, or MOND, which posits that the laws of motion themselves change on immense cosmic scales. This theory suggests that our grasp of gravity is incomplete, and that Newton's laws may not apply accurately at galactic and intergalactic distances. Alternative gravitational theories, some branching from Einstein's general theory of relativity, could also offer new models to account for the gravitational anomalies we observe. Some of these ideas, which even involve extra dimensions of space, might present an entirely new way of looking at the fabric of spacetime. Another possibility is that galaxies are gravitationally self-contained systems, not requiring any extra, invisible mass to explain their stability and rotation, which would mean the processes of galaxy formation are far more intricate than we currently believe. It could also be that undiscovered forms of matter and energy, different from dark matter, are responsible for these large-scale gravitational effects. And while extremely improbable, it's theoretically possible that our interpretation of astronomical data is flawed, leading us to incorrectly infer the existence of dark matter. Ultimately, a universe confirmed to be without dark matter would trigger a profound scientific revolution. the quest for new theories and fresh explanations would become absolutely essential to comprehending the fundamental structure of reality. The velocity of our solar system as it orbits the Milky Way's center is determined by the total mass of every object contained within our orbital path, including all stars, gas, and the significant contribution from dark matter. The solar system's movement is governed by the gravitational pull from this colossal amount of mass, a force that is perfectly counterbalanced by the centrifugal force of its orbital motion, resulting in a stable, nearly circular path around the galactic core. When we discuss the gravitational influence of objects within our orbit, it is crucial to remember this includes not only visible matter like stars, but also the distributed mass of dark matter, which reveals itself only through its gravitational effects. Indeed, the observed rotation of galaxies, including our own, offered some of the earliest and most compelling evidence for dark matter's existence. The rotational speeds far from the galactic center were much faster than could be explained by visible matter alone. This discrepancy strongly suggested the presence of an additional, unseen mass providing the gravity needed to hold these rapidly spinning galaxies together. The mystery surrounding the galactic center remains a captivating subject for astronomers and physicists across the globe. With each passing year, our telescopes grow more powerful, allowing us to probe deeper into this enigmatic region of space. It is here that we hope to find the keys to unlocking many of the fundamental processes that govern our universe. For a considerable time, we knew the location of the galactic center in the constellation Sagittarius. Yet if you had looked, you would have seen no major cosmic objects there. This mystery began to unravel in the early 1930s when Carl Jansky, an engineer at a Bell Telephone Laboratories test site, was investigating sources of radio communication interference. Using a specialized antenna he constructed, he detected a persistent noise of unknown origin whose position shifted across the sky, leading him to conclude, after initially suspecting the sun, that the source lay at the heart of our galaxy, a discovery that laid the very foundation of radio astronomy. Following this breakthrough, Grota Reber, a radio amateur from Wheaton, constructed the first parabolic dish radio telescope in his backyard during the mid-1930s. With his device, he successfully mapped the sky in radio wavelengths, pinpointing bright radio sources and drawing attention to the central regions of the Milky Way. By the early 1950s, these efforts confirmed that a powerful radio source, designated Sagittarius A, was situated extremely close to the galactic center, and by the mid-1960s it was established that a compact nucleus was associated with this source. In the early 1970s, the use of radio interferometry unveiled the complex nature of the Sagittarius radio source. I should explain that this technique revealed that the source comprised two different regions, one that emitted radio waves from non-thermal processes, and another that was a cloud of hot gas. Subsequent studies showed that both areas were enveloped by more hot gas, and one of them, a feature named Sagittarius A star, was identified as having a rotating accretion disk. Until the late 1960s, studying the galactic nucleus was incredibly difficult because dense clouds of cosmic dust absorb visible light, obscuring our view. The advent of infrared astronomy, which can penetrate this dust, finally made it possible to investigate the galaxy's central regions. While early attempts in the 1940s and 60s to locate infrared sources there were unsuccessful, an object was eventually discovered that perfectly matched the size and position of the Sagittarius A radio source, later revealing a more complex structure with multiple components, including nearby stars. By the mid-1970s, astronomers turned their attention to the motion of gas around the galactic center, which they could use to estimate the mass of the presumed object at its core. These observations showed that the gas moved symmetrically at a consistent speed, providing the basis for one of the first attempts to calculate the mass of the central object in our galaxy. As our telescopes grew more powerful, we could soon discern several small sources of infrared light within the gas cloud surrounding the galactic core. Around this time, 2 astronomers compiled a map of this region, identifying 20 such sources, some of which corresponded to the previously detected radio objects. The brightness of these light points varied, but never surpassed a certain threshold, and their sizes and masses also fell within specific ranges, as did their distances from the galactic center. Based on this, the mass of the central object, which was suspected to be a black hole, was estimated. However, I want to emphasize that due to the potential for calculation errors, there was still a chance that no single massive body existed, and that the mass was simply distributed throughout the surrounding area. As observational techniques continued to advance, by the mid-1980s, it became evident that the central black hole was likely located precisely where one of these infrared sources was situated. This conclusion was reinforced by the discovery of 2 large streams of ionized gas in this region, one moving in a circular path around the galactic center, and another following a parabolic trajectory. By measuring the velocity of these streams, the mass of the central object was calculated to be quite substantial. In the early 1990s, the sharp infrared detector became operational at the European Southern Observatory in La Silla, Chile, providing the second to capture infrared images with exceptionally high resolution. The same observatory also housed a spectrometer capable of obtaining 3-dimensional spectra of celestial objects. These advanced tools allowed us, for the first time, to observe individual stars in the central part of our galaxy and study their spectra, revealing that many were surprisingly young, only a few million years old, which contradicted the prevailing belief that star formation was impossible near a massive black hole. This discovery raised a difficult question. Where could the material for these new stars have come from? Scientists theorized that 2 gas rings discovered in the galactic center in the 1980s might be the source, but these rings are not massive enough to directly trigger star formation so close to the black hole. Moreover, the orbits of these young stars do not suggest they formed from the accretion of these rings, leading to a hypothesis that they were born elsewhere in the galaxy and migrated toward its center, their outer layers stripped away by powerful gravitational forces. By the mid-1990s, our observations had identified more than 600 stars near the radio source Sagittarius A star. For approximately 300 of them, we were able to accurately determine their velocities, allowing for a much more precise estimate of the central body's mass, placing it at a few million solar masses within a region just 1/5 of a light-year across. Soon after, even more detailed images from enhanced infrared detectors allowed us to track the movement of over 6,000 stars within 1 parsec of the galactic center. This unprecedented level of precision enabled scientists to calculate the exact trajectories of the stars orbiting closest to the heart of our galaxy. Among this cluster of stars, one in particular, designated S2, would become crucial to our understanding of this extreme environment. Let me tell you about the star S2, which gave us a remarkable view of our galaxy's core. From the early 1990s into the new millennium, it made nearly 2 complete circuits around the central black hole, allowing scientists to precisely map out its orbital characteristics. S2 completes its orbit every 16 years, approaching the black hole at a distance several hundred times greater than that between the Earth and the Sun, which gives you a sense of the immense scale we're talking about. The paths of S2 and other stars in its vicinity largely follow the orbits predicted by Kepler's laws. But you can see clear deviations caused by the effects of general relativity. Since we observe no other significant mass near these stars, it becomes evident that almost all the gravitational influence comes from the central black hole. Through incredibly precise measurements of these orbits, scientists have been able to calculate the black hole's mass with remarkable accuracy. The main source of error in these calculations actually stems from the difficulty of measuring the exact distance from our solar system to the galactic center, located in the Sagittarius constellation. While the gravitational radius of a black hole with this mass is far smaller than S2's closest approach, I can tell you that there's virtually no doubt among scientists that a true black hole, not some other dense cluster of objects, resides at the heart of our galaxy. In the early 2010s, astronomers found something else fascinating. A group of 7 stars orbiting Sagittarius A star from a few light years away, which may be the remnants of a massive star cluster that was torn apart. The way these stars move in relation to each other suggests the presence of an intermediate mass black hole among them. You should also know about the star S62, which gets so close to the central black hole that its speed accelerates to an incredible 10% of the speed of light. To get an even closer look, researchers from Russia and the United States embarked on a major scientific project to study Sagittarius A star. They used a sophisticated network of radio telescopes, some on Earth and others in orbit, aiming to achieve high-resolution imagery of the matter immediately surrounding the black hole. This technology allows them to resolve objects so small they are comparable to a city block set against the vast gas clouds in that region. The initial findings from this project have already confirmed the system's capability to see these tiny inconsistencies, and I know the scientists are planning more observations to capture even more detailed images. In a separate discovery, astronomers using the European Space Agency's Space Telescope found that one of our galaxy's largest clouds is emitting powerful X-ray radiation. This suggests that in the last few hundred years, a very recent period in cosmic terms, the galactic center was the site of far more energetic and brilliant events than what we see today. These discoveries reinforce the idea that Sagittarius A star was likely much more active and luminous in its past. Furthermore, by using specialized instruments on the Very Large Telescope, scientists detected infrared radiation near this massive object, which points to powerful magnetic processes at play. During these observations, they recorded brilliant flares, which I believe were likely caused by matter being whipped around the black hole at tremendous speeds. Back in 2002, scientists spotted a gas cloud which they named G2, heading directly for Sagittarius A star. This cloud is composed primarily of hydrogen and helium, has a mass about 3 times that of Earth, and is much cooler than the stars around it, glowing only because it's illuminated by their ultraviolet radiation. Trajectory calculations predicted that the cloud would have an extremely close encounter with the black hole by the end of 2013. Over the 7 years following its discovery, G2's speed had doubled to an astonishing velocity, and you can imagine the anticipation in the scientific community. There were differing theories on what would happen, with some suspecting a hidden star or even another black hole inside the cloud was helping it withstand the immense tidal forces. Ultimately, when the cloud made its closest approach, nothing dramatic occurred. It remained intact, leading to the conclusion that it likely contains a star, or perhaps even a pair of merged stars. Meanwhile, scientists from Japan announced the discovery of another exceptionally heavy object at our galaxy's center, which they suspect might be a black hole. This object is located about 200 light-years from the core of the Milky Way, and along with its surrounding cloud, it spans a region about 3 light-years across. Its mass is estimated to be no more than 100,000 times that of our Sun, but it's still uncertain if this is truly a black hole or another type of celestial body. More recently, Japanese astronomers detected a black hole in the galaxy's central region that is comparable in size to Jupiter, but weighs approximately 32,000 times more than the Sun. This object, situated near the radio source known as Sagittarius A star, is now considered the third example of an intermediate mass black hole identified at the galactic center. Finally, for their groundbreaking work on Sagittarius A star, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics in 2020, as their research proved that an incredibly dense and massive object, for which a supermassive black hole is the only plausible explanation, occupies the center of our galaxy. In 2006, I had the opportunity to familiarize myself with reports from future Nobel laureates on supermassive black holes while I was at Harvard as an independent science writer. It was this experience, along with several other conferences, that prompted me to write my book, The Undetermined Universe, which delves into the boundaries of human knowledge. The groundbreaking discovery that earned the Nobel Prize was the culmination of many years of dedicated observation and meticulous research. Utilizing adaptive optics and infrared astronomy, the teams, led by Genzel and Ghez, were able to meticulously map the movements of stars very close to the center of our galaxy. They observed that these stars followed orbital paths that could only be accounted for by the presence of an incredibly massive, virtually invisible object. Its profound gravitational pull was the only logical explanation for the stellar trajectories they were witnessing. The research conducted by these two scientific groups delivered undeniable proof that such a colossal object resides at the heart of the Milky Way. This finding carries immense weight for astrophysics, enhancing our comprehension of galactic cause and the forces that shaped their behavior. Furthermore, it validates the existence of supermassive black holes, which continue to be among the most enigmatic objects known to science. More recently, humanity captured an actual image of Sagittarius A star, the black hole at our galaxy's center. This remarkable achievement was the result of an international project called the Event Horizon Telescope, a global network of radio telescopes synchronized to function as a single Earth-sized observatory. This innovative method gave astronomers their very first glimpse of an event horizon, the threshold beyond which nothing, including light, can escape a black hole's gravitational grasp. The resulting image serves as a significant validation of our current theories on black holes and is a direct confirmation of Einstein's general theory of relativity. What you see in the photograph is the silhouette of the black hole, which appears as a shadow cast by the light that bends around it, warped by its intense gravitational field. This picture is not merely evidence that black holes are real. It is also an invaluable instrument for investigating the physical processes that unfold in the universe's most extreme environments, creating new avenues to explore gravity, fundamental interactions, and cosmology. Ever since this discovery, astronomers and physicists have persistently monitored the object at the galaxy's center, aiming to better understand its properties and its function in galactic dynamics. The investigation of Sagittarius A star has vastly broadened our understanding of black holes, marking a pivotal moment in our comprehension of the universe's structure. A black hole itself is a volume of space-time where the gravitational attraction is so overpowering that once something crosses the boundary called the event horizon, it can never leave. Because the escape velocity near a black hole's event horizon surpasses the speed of light, the theory of relativity dictates that nothing can ever break free from its grip. The terms black hole, dark matter, and dark energy frequently lead to confusion because of their similar names, but they describe entirely separate phenomena in the fields of astronomy and cosmology. A black hole is a cosmic body with gravity so intense that nothing can escape it, forming from ordinary matter when, for instance, a giant star collapses under its own mass. Dark matter, on the other hand, is a theoretical type of matter that doesn't interact with light or any other form of electromagnetic radiation, making it impossible to observe directly. Its existence was theorized to explain gravitational phenomena, like the rotation of galaxies, that visible matter alone cannot account for. Meanwhile, dark energy is a mysterious force thought to be responsible for the accelerating expansion of the universe. It constitutes the majority of the universe's total energy and works against gravity over vast cosmic distances. So, while all three concepts relate to poorly understood aspects of our universe, they represent fundamentally different things. Black holes are localized concentrations of mass that warp space-time around them. Dark matter is a pervasive substance whose gravitational influence is felt on a cosmic scale, but remains unseen. And dark energy is a property of space itself that is pushing the universe apart at an ever-increasing rate. Clearly understanding these distinctions is crucial for accurately interpreting the physical workings of the cosmos. The name black hole can itself be quite deceptive, as it implies a void or an emptiness. In truth, black holes are areas of incredibly high mass and gravitational concentration. The term was not coined by scientists, but rather became popular in the public imagination. The scientific view is that they are not holes at all, but are instead unimaginably dense points of mass, where the gravitational force is so absolute that nothing can get out after passing the event horizon. They are better imagined as black spheres or even black stars, an idea put forth by early theorists like John Michell. John Michell was an English natural philosopher from the 18th century who made substantial contributions to astronomy, geology, and seismology, and he is recognized as one of the forerunners of the black hole concept. In 1783, Michell proposed the hypothetical existence of dark stars, celestial bodies with gravity so powerful that light itself could not escape from their surface. His entire idea was formulated based on the principles of Newtonian gravity. He theorized that if a star possessed enough mass within a small enough radius, the velocity needed to escape its gravity would surpass the speed of light, making the star invisible from a distance. Michell even suggested a way to identify these cosmic bodies by observing their gravitational pull on nearby visible stars. The name black hole came into use much later, introduced in 1967 by American theoretical physicist John Archibald Wheeler, who foresaw the existence of such gravitationally extreme objects resulting from stellar collapse. It's still debated whether Wheeler invented the term himself or simply adopted a fitting phrase from someone in the audience during a lecture. But since that time, black holes have deeply fascinated the human mind. Nevertheless, it was Michel's pioneering research that established the groundwork for all future discoveries in this area. As far back as 1915, Albert Einstein's general theory of relativity gave rise to the Einstein field equations, which describe gravitational fields. That very same year, Carl Schwarzschild derived one of the first exact solutions to these equations. This solution indicated that there must be areas in the cosmos where the gravitational pull is so immense that nothing, not even particles of light moving at maximum velocity, can break free. At the time, these astrophysical phenomena were referred to as collapsed stars or frozen stars. You might find that alternative names, such as light trap or supermassive object, more accurately capture the true nature of black holes. The term light trap highlights their defining ability to ensnare even photons, the fastest particles in our universe, while supermassive object underscores their incredible mass and gravitational power. The scientific community often adopts terms based on historical origins or suggestions from prominent researchers, and these names don't always best describe an object's characteristics. In the case of black holes, the name has become firmly established and is widely used, though it can sometimes create confusion for those outside the field of astrophysics. Carl Schwarzschild produced a solution for Einstein's equations that details the gravitational field surrounding a non-rotating, spherically symmetric object, specifically a black hole. Schwarzschild discovered this solution in 1916, not long after Einstein had published his theory. His findings revealed a particular radius, now called the Schwarzschild radius, inside which gravity becomes so powerful that nothing, including light itself, can escape. This boundary defines the very essence of a black hole, marking the critical radius of the event horizon for a non-rotating black hole, as seen by an external observer. Anything that passes beyond this radius seems to be frozen in time and becomes entirely invisible. This discovery was among the first precise solutions to Einstein's equations and was instrumental in shaping our subsequent understanding of black holes and the relativistic effects that occur near such extreme masses. Scientists categorize black holes in various ways, for instance, distinguishing between stellar black holes, which are formed from the collapse of stars, and supermassive black holes. These supermassive black holes are typically located at the centers of galaxies and possess masses millions or even billions of times greater than our Sun. While these classifications offer a more precise description, the term black hole remains the most familiar and widely recognized name in common language. It's crucial for you to understand that black holes are not empty voids in space. They contain an enormous amount of mass packed into a very small volume. Their existence can be verified through indirect evidence, like their gravitational effects on nearby objects or the intense radiation emitted by matter being drawn into them. Escape velocity is the absolute minimum speed an object needs to break free from the gravitational pull of a planet or another celestial body without falling back. For our planet, Earth, this speed is roughly 11.2 kilometers per second. If you could propel an object, like a rocket, at or above this velocity, it would be able to achieve orbit or leave Earth's gravitational influence entirely to travel deeper into space. Now, when you consider far more massive bodies like stars, their escape velocities are substantially greater. At a certain stage, if a sufficiently massive star depletes its nuclear fuel, its own internal gravity can become so overwhelming that it triggers a collapse, which can ultimately lead to the formation of a black hole. The term black hole has undeniably permeated popular culture, giving rise to numerous myths and speculative ideas about time travel, wormholes, and gateways to other universes. While these notions are captivating, they primarily exist within the domains of theoretical physics and science fiction. Certain theoretical models suggest that the singularity at the heart of a black hole could function as a bridge or tunnel to another point in space or time, a concept often linked to wormholes. Wormholes are hypothetical features of space-time that could theoretically offer a shortcut for interstellar travel. These ideas emerge from general relativity, with the equations describing them first appearing in solutions by Kerr and others. However, the actual existence of wormholes, their stability, and whether they could ever be used for travel are subjects of intense research and debate. Most theoretical frameworks for wormholes depend on the presence of exotic matter possessing negative energy to hold the tunnel open. This type of matter would need to exhibit properties that have never been observed experimentally or explained by the standard model of particle physics. Moreover, the conditions inside a black hole, especially at the singularity, are so extreme that our current physical theories are unable to describe them adequately. A complete understanding likely awaits a theory of quantum gravity that can successfully merge general relativity with quantum mechanics. At the very heart of a black hole, you will find a point of theoretically infinite density called a singularity, a place where the known laws of physics simply break down. To even begin to conceptualize this point, physicists like myself must rely on theories of quantum gravity, which are our most promising attempts to unify quantum mechanics with the force of gravity. One prominent idea is string theory, which suggests that matter's fundamental components are not particles, but one-dimensional strings, whose vibrations dictate the various fundamental forces. Within this framework, it's proposed that singularities might be smoothed out in the extra dimensions the theory requires. Another leading approach, loop quantum gravity, posits that spacetime is constructed from incredibly small, discrete loops, forming a network that prevents the possibility of infinite density and replaces the singularity with a concept known as a big bounce. There are also a number of modified theories of gravity that propose alterations to general relativity, specifically to avoid the formation of black holes, singularities inside black holes. These concepts suggest that black holes might contain regions of extremely high density that never actually reach infinity. This area of study is expanded by quantum cosmology, a discipline that applies quantum rules to the universe at large, exploring possible quantum states that could replace the classical singularity with less severe conditions. I must emphasize to you that all these theories are the subject of vigorous research and remain under development. They present different explanations and potential solutions to the singularity problem, yet not a single one has achieved universal acceptance or received any definitive experimental validation. Black holes are truly unique objects in the cosmos that showcase a variety of relativistic properties, as they create extreme environments where gravity is potent enough to profoundly alter spacetime. General relativity predicts that mass warps the spacetime surrounding it, and black holes bend it so intensely that nothing, not even light, can escape this distortion, which forms their famous event horizon. You should understand that the event horizon is not a physical surface, but rather a mathematical line of demarcation. For you, as an external observer, any object approaching this boundary would appear to slow its motion and seem to never quite cross it. This is directly related to time dilation, where time itself passes more slowly within a strong gravitational field. Consequently, near a black hole's event horizon, this effect becomes so extreme that time appears to nearly halt from a distant vantage point. Another effect is gravitational redshift, a phenomenon where light emitted from a powerful gravitational field loses energy, causing its spectrum to shift toward the red end. This means photons originating near a black hole will look less energetic and therefore redder to you than they were at the moment of their emission. Similarly, the orbits of stars or particles around a black hole are not the clean ellipses predicted by Newtonian physics, a deviation we call relativistic orbital precession. Relativistic precession, sometimes called perihelion precession, is a core prediction of Einstein's general theory of relativity that describes how the orbital path of a body gradually shifts due to the curvature of spacetime near a massive object. The classic example that I always point to is the precession of Mercury's perihelion. Its orbit doesn't close on itself as Newton's laws suggest, but instead, its closest approach to the Sun shifts with each revolution. A problem that baffled astronomers until Einstein's theory accurately predicted it, providing crucial early evidence. The region surrounding a black hole, where gravity hasn't yet become inescapable, is known as the accretion disk. Here, you can observe matter circling the black hole, heating up intensely due to friction as it spirals inward, and emitting powerful radiation across a broad spectrum, including X-rays and visible light. It is by observing this very radiation that you and I, as astronomers, are able to detect and study black holes, since the objects themselves are completely dark. So, you can think of the event horizon as the ultimate boundary beyond which no event can be seen, because the gravitational pull has become stronger than the speed of light. It's a point of no return. An object crossing it would not feel anything unusual at the moment of passage, but from that point on, its fall toward the singularity is irreversible, and it can no longer send information outward. For you, as a distant observer, time would seem to stop for that object right at the horizon. But this is an illusion, as the object itself would experience time passing normally on its final journey. From the perspective of any object, time continues its normal course within its own frame of reference. For an astronaut, this means they could pass through the event horizon without any immediate awareness of a change in their local environment. The term spaghettification aptly describes the process where an object entering a region of powerful gravity, such as a black hole, is elongated and compressed. This name originates from the way extreme gravitational tidal forces stretch the object along one axis, much like a strand of spaghetti. To understand how this works, picture an object as it nears a black hole. With decreasing distance, the gravitational pull on the part of the object closer to the black hole becomes substantially stronger than the pull on the farther part. This disparity in force generates what are known as tidal forces, which, in the case of black holes, can be so powerful that they cause the object to stretch dramatically toward the black hole's center, while simultaneously squeezing it from the sides. For a celestial body like a star or planet, this deformation can ultimately lead to its complete annihilation. Spaghettification is a direct result of the black hole's non-uniform gravitational field, which is significantly more potent at the end, nearer to the black hole, than at the one farther away. Although this phenomenon can technically happen near any massive body, only black holes are capable of producing tidal forces strong enough for such startling effects. This process is especially pronounced for stellar mass black holes, as the tidal forces at their event horizons are far more intense than those of their supermassive counterparts. In fact, around supermassive black holes, these forces can be so weak that an object might cross the event horizon without undergoing significant spaghettification, until it approaches the singularity itself. In principle, there is no absolute theoretical limit to the mass a black hole can attain. Its mass can conceptually grow indefinitely as it consumes matter and other cosmic objects, including stars, gas, dust, and even entire star systems or other black holes. However, certain factors do impose practical constraints on this growth. Supermassive black holes, which reside at the centers of galaxies, can possess masses equivalent to billions of suns. While they could theoretically become even larger, their expansion is restricted by both the amount of available matter in their vicinity and the speed at which they can accrete it. As matter plunges into a black hole, it heats up and radiates energy. If this process occurs too quickly, the resulting radiation can generate enough pressure to repel other incoming matter, thereby slowing the black hole's rate of growth. This phenomenon is referred to as radiation-efficient accretion and creates certain limitations, often called Eddington limits. Cosmological constraints, which concern the growth and evolution of the universe as a whole, may also play a role. And while it is hypothesized that black holes might eventually evaporate through a quantum process called Hawking radiation, this effect does not currently constrain their growth in our present-day universe, as astronomers continue to find ever more massive black holes, helping to refine our theories. Black holes are broadly classified as either stellar or supermassive, a distinction based primarily on their mass, which in turn dictates their properties and formation pathways. Stellar black holes are forged from the gravitational collapse of enormous stars at the conclusion of their life cycles. When a star with sufficient mass runs out of nuclear fuel, it can no longer support itself against its own gravity and implodes, sometimes resulting in the formation of a black hole with a mass ranging from a few to several dozen times that of our Sun. In contrast, supermassive black holes boast masses from millions to billions of times that of the Sun, and are typically found at the hearts of galaxies. The precise mechanism of their formation remains an open question in astrophysics. Existing theories propose scenarios such as the rapid accumulation of matter in the early cosmos, the collapse of vast gas clouds, with a successive merging of many smaller black holes. Despite these differences, the scientific consensus is that they are fundamentally the same type of cosmic object, described by the same principles of relativistic physics, though there might be some qualitative distinctions in their magnetic fields or accretion methods. This remains a vibrant field of study. Investigating supermassive black holes is crucial to modern astrophysics, because these enigmatic objects inhabit the centers of almost all large galaxies and profoundly shape their structure and evolution. Objects like Sagittarius A star, the supermassive black hole at the center of our own galaxy, dictate the orbits of stars and gas on a galactic scale, and their activity can even control the rate of star formation. Studying the processes near these giants provides scientists with vital clues about how galaxies develop and how accretion, the infall of matter into a black hole, unleashes immense quantities of energy. Furthermore, supermassive black holes offer an unparalleled natural laboratory for testing Albert Einstein's general theory of relativity under the most extreme gravitational conditions imaginable. They are also instrumental in exploring the properties of gravitational waves and other fundamental aspects of physics that are otherwise difficult to probe experimentally. Beyond this, they may even hold the key to understanding dark matter, as certain processes, such as the annihilation of dark matter particles, could theoretically occur around black holes and produce observable radiation, giving us a new window into this mysterious substance. Several compelling theories attempt to explain the origin of Sagittarius A star. One hypothesis suggests it all started with stars and star clusters forming at our galaxy's core, which eventually collapsed and merged, accumulating matter to become the supermassive object it is today. An alternative idea proposes that it could have formed directly from the collapse of an immense gas cloud, skipping the intermediate stellar stages entirely. A third possibility is that a much smaller black hole steadily grew to its current proportions by feeding on surrounding matter and merging with other black holes within the dense galactic center. The event horizon of Sagittarius A star spans a radius of approximately 22 million kilometers, which is about 120 times the radius of our Sun, though this value can fluctuate depending on the black hole's rotation and its interactions with the surrounding cosmic environment. Observing the galactic center has historically been a significant challenge. Early on, astronomers had to use radio and infrared wavelengths to cut through the dense clouds of gas and dust. But as telescope technology advanced, offering greater sensitivity and resolution, our view became increasingly precise. A crucial turning point came with the creation of the Event Horizon Telescope, or EHT, a global collaboration of radio observatories that function as a single, virtual telescope the size of Earth. This network employs a method known as very long baseline interferometry to synthesize data from around the world, achieving an incredible level of detail. This innovative approach made it possible to directly observe the event horizon and capture the very first image of a black hole, revealing a luminous ring of light warped by gravity around the object's dark central shadow. More recently, a study from astrophysicist Raju Pul at the Seoul National University of Science and Technology explored the fascinating concept of black hole mimics. Using the latest EHT observations of Sagittarius A star, his team investigated whether a different kind of cosmic object could produce a similar image. The shadow you see in that famous picture is far more than just a dark patch. It represents a zone of gravity so intense that light itself cannot break free, while the light just outside this region is bent to create the signature ring-like effect. The researchers focused on two potential mimics, comparing the shadows they would theoretically cast to the actual shadow observed at our galaxy's center. The analysis showed that one of these objects could indeed generate a shadow that closely resembled the one from Sagittarius A star. However, the parameters of the second object were such that its shadow was inconsistent with the observation. While this discovery doesn't disprove that a black hole resides at the galactic center, it encourages us to study these cosmic shadows with even greater scrutiny as we await future data that may clarify these possibilities. Looking forward, a team of astrophysicists from Harvard University intends to track the movement of a superheated region of gas, known as a hotspot, as it orbits near Sagittarius A star. With a novel imaging algorithm, their goal is to produce dynamic images that show how this hotspot moves and deforms on its journey. To capture this with the required accuracy, the team plans to use the next-generation expanded network of the Event Horizon Telescope, which will vastly improve our ability to observe the hotspot's changing shape and orbital phases. This groundbreaking research is poised to deepen our understanding of the fundamental physics at play in the immediate vicinity of a supermassive black hole. The insights gained could significantly impact our knowledge of astrophysics, particularly how matter behaves under such extreme conditions and the intricate mechanisms of gravitational interaction. Such advances continue to refine the very methods we use to find these invisible giants, as we cannot see them directly with traditional telescopes. Because they are invisible, detecting black holes requires indirect methods. One common technique is to analyze the motion of nearby stars and gas. If they are moving at unusually high speeds, it strongly implies the gravitational influence of a massive, unseen object. Another way to detect a black hole is by observing its interaction with surrounding material. As matter falls toward a black hole, it forms a superheated accretion disk that radiates intensely in the X-ray and sometimes gamma-ray spectrums, creating a bright signature that our space-based observatories can identify. Another way you can detect a black hole is by observing a phenomenon called gravitational lensing. The immense gravity of a black hole can warp the path of light from a distant star, creating distinctive arcs or ring-like patterns in images. Furthermore, recent breakthroughs in astrophysics, such as the historic imaging by the Event Horizon Telescope, have shown it's possible to see a black hole's shadow, which is formed by light bending around its edge. This success has ushered in a new chapter for investigating these amazing cosmic entities. The radiation we see from supermassive black holes doesn't come from the black holes themselves, as they emit no light, but originates from the matter swirling in an accretion disk. You can picture this disk forming as stars, gas, and dust are captured by the black hole's powerful gravitational influence. As this material spirals inward, friction and other energetic forces cause it to heat to extraordinary temperatures, making it glow intensely with X-ray and ultraviolet radiation. Interestingly, not all of this material is consumed. Some of it can be violently expelled back into space as powerful jets. These jets, depending on their velocity and makeup, can radiate energy across the entire electromagnetic spectrum, from radio and infrared to visible, ultraviolet, and X-ray wavelengths. Extending for thousands of light years, these jets have a profound effect on the surrounding interstellar medium and can even influence the rate of star formation. Observations of these emissions provide scientists with a window into the physical processes occurring near black holes, enabling them to model how matter is accreted. This also helps us understand how the energy released impacts larger structures, such as the galactic environment and the evolution of the galaxy itself. A truly unique astrophysical event involves hypervelocity stars, which are ejected by the supermassive black hole Sagittarius A star at the center of our own galaxy. These stars achieve their astonishing speeds through dynamic encounters in the extreme gravitational field close to the black hole. When a star or another celestial object passes too close to the supermassive black hole, it can be accelerated to a velocity so high that it escapes the galaxy's gravitational grip entirely and is flung into intergalactic space. This gravitational slingshot effect can happen, for instance, when a pair of stars has a close call near the black hole, resulting in one being catapulted away. The discovery and analysis of these hypervelocity stars are crucial for understanding the complex gravitational dynamics at the hearts of galaxies. Accretion. The mechanism by which matter is drawn toward a black hole is fundamental to comprehending their growth and luminosity. As stars or clouds of gas and dust venture within a black hole's gravitational reach, they are gradually pulled inward, often forming that rotating accretion disk. The material in this disk spirals toward the black hole, and the intense friction involved heats it to tremendous temperatures, causing it to emit powerful radiation, mostly in the X-ray and ultraviolet parts of the spectrum, which shines brightly against the dark backdrop of space. This entire process of matter accreting onto supermassive black holes can be one of the most energetic events in the universe. It might surprise you to learn that the efficiency of converting mass into energy within these accretion disks is significantly higher than in the nuclear fusion that powers stars. Nuclear fusion, like the process that turns hydrogen into helium in a star's core, converts at most about 7% of the mass into energy, according to Einstein's equation E equals mc squared. In stark contrast, the process of accretion onto a black hole can theoretically convert up to approximately 10% of the infalling matter's mass equivalent into energy. It is vital to recognize, however, that the matter's mass itself is not directly transformed into energy. Instead, the mass falls into the black hole, adding to its total, while the energy you see is the release of gravitational potential energy in the form of radiation. This is particularly true for rotating black holes, known as Kerr black holes, whose properties were first described by the scientist Roy Kerr in 1963. The critical distinction between a Kerr black hole and a simple non-rotating one, a Schwarzschild black hole, is that the Kerr type is defined by two primary parameters, its mass and its rotation. While mass dictates the strength of its gravitational pull, its rotation means the black hole spins on an axis, dragging the fabric of space around with it. The Kerr metric, a solution to Einstein's field equations of general relativity, mathematically describes the gravitational field surrounding such a rotating, uncharged black hole. Because most black holes in the universe are likely to be rotating, the Kerr metric offers a more complete and realistic description than the Schwarzschild metric, which only applies to non-rotating black holes. A Kerr black hole also features a different kind of singularity. Instead of all its mass being crushed into an infinitely small point, it has a ring singularity. This ring is enclosed by the event horizon, the ultimate boundary from which nothing, not even light, can escape the black hole's overwhelming gravitational pull. I want to tell you about another area surrounding a Kerr black hole, known as the ergosphere, a fascinating region that only forms around rotating black holes. This zone is situated just outside the event horizon, in a place where space-time itself is unavoidably dragged along by the black hole's spin. You can imagine that inside the ergosphere, the fabric of space is distorted and swirls as if it were attached to a spinning sphere. Consequently, any object that enters this region, even light, is forced to rotate in the same direction as the black hole, making it impossible to remain still relative to the distant universe. Many astronomers theorize that the centers of galaxies are home to Kerr black holes, since these objects are observed to rotate and actively pull in nearby matter. This process of matter accretion is one of the most efficient energy conversion mechanisms in the cosmos, surpassed only by matter-antimatter annihilation, where a full 100% of mass becomes energy. For instance, you can see this power in active galactic nuclei like quasars, which radiate with immense force as matter spirals into the supermassive black holes at their hearts, often shining so brilliantly that they completely overwhelm the light of their entire host galaxy. Next, I need to bring up the concept of Hawking radiation, a process predicted by quantum field theory and curved spacetime, which suggests that black holes can emit particles and in doing so lose mass. This idea directly challenges the classical view of black holes as inescapable cosmic prisons. However, quantum mechanics allows for the spontaneous creation of particle-antiparticle pairs from the vacuum near the event horizon. If one of these particles slips past the horizon while its partner escapes, it effectively robs the black hole of a tiny amount of energy, causing its mass to diminish over time. You can understand the core of Hawking radiation by using the idea of quantum tunneling. Within quantum mechanics, particles behave like waves and have the ability to pass through energy barriers that would be insurmountable in classical physics. When applied to black holes, this means that virtual particles, which flicker in and out of existence in the vacuum due to Heisenberg's uncertainty principle, can occasionally form near the event horizon. One particle from the pair might get trapped by the black hole's gravity, while the other manages to break free into space. For this radiation to occur, the escaping particle must become real, which happens when it moves away into space. To maintain the law of conservation of energy, the particle that falls into the black hole must possess negative energy from an outside observer's point of view, which in turn reduces the black hole's total mass energy. This entire process results in the very slow evaporation of the black hole itself. I should note that this is a simplified analogy. A precise mathematical understanding requires advanced knowledge of quantum field theory in curved spacetime. Due to its extreme faintness, Hawking radiation has never been detected on an astronomical scale. The prediction itself arises from merging general relativity with quantum mechanics, and, despite the absence of direct sightings, there is compelling indirect evidence. For example, some physics experiments have simulated the conditions near an event horizon using sound waves and fluids, creating what are called analog black holes. These laboratory setups have produced a form of radiation that behaves just like the predicted Hawking radiation, supporting the underlying theory. The theory is also bolstered by thermodynamic analogies, where the laws governing black holes mirror the laws of thermodynamics, attributing them with properties like temperature and entropy. This connection strengthens our confidence that Hawking radiation is a real phenomenon. Looking to the future, new developments in gravitational wave astronomy are giving us powerful tools to probe the nature of black holes, which might eventually allow us to spot effects linked to this radiation. Nevertheless, directly confirming it remains one of modern astrophysics' greatest challenges. Now, let's discuss a completely separate phenomenon tied to supermassive black holes: astrophysical jets. These are immense, powerful streams of charged particles that are launched from active galactic nuclei. Jets can form when material from the surrounding accretion disk interacts with the powerful magnetic fields that are twisted by the black hole's rotation. The resulting magnetic forces are strong enough to funnel some of that matter and radiation along the black hole's rotational axis, blasting it into space across unimaginable distances. A prime example in our own cosmic neighborhood is the supermassive black hole Sagittarius A star, which resides at the center of the Milky Way. Its immense gravitational force profoundly shapes the local star population, corralling them into a dense, rapidly moving cluster. Within this group are the S stars, which you can observe traveling at incredible speeds along highly elongated elliptical orbits, all held in place by the central black hole's pull. Some celestial bodies venture so near the black hole that they come under the influence of immense tidal forces. As we've noted, the accretion disk enveloping the black hole can also vigorously engage with adjacent gas clouds, thereby accelerating star-forming activities within this zone. Furthermore, the black hole's gravitational field is capable of launching hypervelocity stars, which, given the right circumstances, can be ejected from the galactic core or even from the galaxy entirely at tremendous speeds. These phenomena, all propelled by the supermassive black hole, establish a singular environment that governs the dynamics and life cycles of stars in the galactic nucleus, providing essential clues to how matter and energy are exchanged between the central black hole and its cosmic surroundings. In the heart of the galaxy, gas clouds are subjected to the colossal gravitational pull of both the supermassive black hole, Sagittarius A star, and other massive objects in the vicinity. Their movement is defined by incredible velocities and intricate paths, which are often nonlinear and influenced by collisions and encounters with other celestial bodies, including stars and star clusters. The gravitational sway of the black hole can trigger the formation of accretion flows, funneling gas clouds inward and causing a surge in the density and temperature of matter. This process can either spark the birth of new stars or, conversely, lead to the obliteration of existing ones. The motion of these gases is also fundamental to distributing angular momentum and sustaining the accretion processes that feed the black hole's growth and activity, making them active agents in sculpting the structure and evolution of the galaxy's central region. The supermassive black hole at our galaxy's center, Sagittarius A star, exerts a profound influence on neighboring star clusters. This impact stems from the black hole's direct gravitational pull, the dynamics of its accretion disk, and the intense radiation produced near the event horizon. These interactions can warp the orbits of stars within the clusters, and the clusters themselves can be stripped of their outer stellar layers by powerful tidal forces. Star clusters can also experience a phenomenon known as dynamical relaxation, where heavier stars sink toward the cluster's core while lighter ones are flung out due to complex gravitational interplay. Moreover, accretion can draw matter from these clusters into the black hole's disk, which in turn amplifies the radiation in the galactic center and affects the conditions for star formation in the nearby interstellar medium, revealing a complex dance that is vital to the evolution of the galactic core. Calculating the mass of Sagittarius A star through the analysis of stellar dynamics stands as one of the most direct and trustworthy methods for determining the supermassive black hole's properties. Researchers meticulously observe the movements of stars orbiting close to the black hole, using Kepler's laws and the principles of general relativity to model their trajectories. By examining the shifts in these stars' positions and velocities, scientists can deduce the strength of the black hole's gravitational influence and, from there, calculate its mass. This technique has been successfully applied in observational projects using powerful instruments like the Keck telescopes and the Very Large Telescope, which have enabled precise measurements of the orbital parameters of the S-class stars near Sagittarius A star. These findings have not only confirmed the presence of an incredibly massive, compact, and non-luminous object consistent with a black hole, but have also allowed its mass to be estimated at several million times that of our Sun, reinforcing the critical role supermassive black holes play in the dynamics of galactic centers. According to astronomical observations and sophisticated computer simulations, our Milky Way and the neighboring Andromeda galaxy, also known as M31, are on an unavoidable collision course, drawn together by their mutual gravitational attraction. They are approaching each other at a speed of approximately 100 to 110 kilometers per second, with the initial encounter predicted to start in about 4 billion years. This cosmic event will not be a catastrophic crash in the way we imagine planetary collisions. The immense distances separating stars make direct physical impacts exceptionally rare. Instead, the powerful gravitational interactions will profoundly remold the structure of both galaxies. Over a vast span of gravitational interplay and merging, the Milky Way and Andromeda are expected to coalesce into a single, gigantic elliptical galaxy, a transformation that will unfold over billions of years. Following the collision of the Milky Way and Andromeda, their central black holes will begin a process of merging. It is highly probable that they will ultimately collide and fuse into a single, more massive black hole. This merger is a complex and monumental event that releases tremendous energy in the form of gravitational waves. The resulting black hole will possess a mass roughly equivalent to the combined masses of its predecessors, less the energy radiated away by these gravitational ripples. This climactic event will not substantially alter the overall structure of the newly formed galaxy, as black holes represent only a tiny fraction of the total mass and scale of their galactic hosts. The black hole at the heart of our Milky Way, Sagittarius A star, currently possesses a mass equivalent to about 4 million suns. In contrast, Andromeda's central black hole, M31 star, is estimated to have a mass around 140 million solar masses. Consequently, the combined black hole post-merger will have a mass of approximately 144 million solar masses, though the final value will be influenced by factors like the precise mass of each black hole at the moment of fusion and the energy shed as gravitational waves, which typically accounts for a minor portion of the total mass. The collision of galaxies can trigger the awakening of their central black holes. If the merger process funnels enough gas toward these black holes, it can initiate a phase where they consume matter so voraciously that their surroundings blaze with incredible light. These phenomena are known as active galactic nuclei, with quasars being the most luminous examples. While quasars were far more prevalent in the early cosmos, they are now a rare sight, typically linked to galaxies undergoing active mergers and matter accretion. Quasars were first detected in the 1960s, thanks to their peculiar radio signals and visual characteristics. They initially presented as enigmatic radio sources that looked like simple stars through optical telescopes, but they were soon revealed to be something far more extraordinary. The breakthrough came in 1963, when astronomer Martin Schmidt of the California Institute of Technology observed that a quasar's spectral lines were shifted toward the red end of the spectrum to an unprecedented degree, implying it was located at an immense distance from our planet. This extreme redshift, when interpreted as a consequence of the universe's expansion, led to the name quasar, a contraction of the English term quasi-stellar radio source. The prefix quasi originates from a Latin word meaning as if or almost, which perfectly captured how these objects mimicked the appearance of stars in telescopes while also emitting powerful radio waves. It was later discovered that not all quasars are strong radio emitters, and the term evolved to describe any supremely luminous galactic nucleus, regardless of its radio output. The accepted modern definition describes a quasar as an active galactic nucleus with an exceptionally high luminosity, often outshining all the stars in its host galaxy combined. In the context of the Milky Way and Andromeda merger, it is theoretically possible for a quasar-like object to form if the colliding black holes accrete a sufficient amount of gas. However, since both are mature galaxies with limited gas reserves to fuel such an event, the likelihood of a true quasar emerging from this cosmic collision remains low. Should humanity's descendants still inhabit Earth when the Milky Way and Andromeda finally collide, they would witness a truly magnificent celestial event. In the merger's early stages, Andromeda would grow progressively larger and more brilliant in the night sky, eventually dominating a vast portion of it. The familiar starscape would be transformed as the stars and gas clouds of both galaxies begin to weave together, creating a new and unfamiliar celestial tapestry. As the galaxies actively interact and collapse into one another, you could expect to see a surge in the formation of new star clusters across the sky. The heavens might even become brighter overall, illuminated by intense regions of starbirth and a higher frequency of supernovae triggered by the powerful gravitational disturbances. Despite the cosmic drama, this galactic fusion is an extremely gradual process that will unfold over billions of years, with changes to the night sky occurring slowly across countless generations of observers. The Earth, the Sun, and our entire solar system will most likely emerge from this merger unscathed, as the sheer distances between stars make direct collisions exceptionally rare. There is, however, a remote possibility that our solar system could be gravitationally flung into a different region of the newly formed galaxy, or perhaps even cast out into the emptiness of intergalactic space. The peak brightness a black hole can achieve is directly tied to the quantity of matter it consumes. When a black hole accretes matter, that material heats up and radiates intensely just before it passes the event horizon and vanishes forever. This luminosity can become staggering, particularly when the black hole is actively feeding on gas and stars. During a galactic merger, this accretion process can be greatly amplified, as vast amounts of gas are funneled toward the central region where the black hole is located, potentially pushing its brightness to incredible levels. If the accretion rate reaches its maximum theoretical value, known as the Eddington limit, the black hole's luminosity can rival that of the brightest quasars in the universe. This limit represents the point where the outward pressure from the light an object emits perfectly balances the inward pull of its own gravity on surrounding material. This concept is named for the English astrophysicist Arthur Eddington, who first described this delicate equilibrium. Within the context of a black hole's accretion disk, should the disk's luminosity surpass the Eddington limit, the intense radiation pressure will begin to drive matter away, effectively throttling the inflow of material. This mechanism establishes a natural cap on how quickly a black hole can feed. For a supermassive black hole like the one in our galaxy's center, the Eddington limit provides a way to calculate the absolute maximum luminosity it could attain during a period of intense accretion. When a supermassive black hole starts consuming matter at a rate near the Eddington limit, it can flare up with intense brightness, triggering what we call quasar activity. The light from a quasar can outshine its entire host galaxy by hundreds or even thousands of times. The exact brilliance of this phenomenon, however, is governed by several factors, including the black hole's mass, the volume and configuration of the material it accretes, and the complex physical processes unfolding in the accretion disk nearby. While the active galactic nucleus formed by the merger of the Milky Way and Andromeda would be incredibly powerful, its light would not appear brighter than the moon in our sky. This is purely a matter of the immense distance to the galactic center, which is about 25 to 28,000 light-years away. For comparison, the moon seems so bright simply because of its proximity, whereas the universe's most powerful quasars, billions of light-years distant, are reduced to mere faint specks in our telescopes. While the active galactic nucleus formed by the merger of the Milky Way and Andromeda would be incredibly powerful, its light would not appear brighter than the moon in our sky. This is purely a matter of the immense distance to the galactic center, which is about 25 to 28,000 light-years away. For comparison, the Moon seems so bright simply because of its proximity, whereas the universe's most powerful quasars, billions of light-years distant, are reduced to mere faint specks in our telescopes. While the active galactic nucleus formed by the merger of the Milky Way and Andromeda would be incredibly powerful, its light would not appear brighter than the Moon in our sky. This is purely a matter of the immense distance to the galactic center, which is about 25 to 28,000 light-years away. For comparison, the Moon seems so bright simply because of its proximity, whereas the universe's most powerful quasars, billions of light-years distant, are reduced to mere faint specks in our telescopes.
Still, if the activity at the heart of the merged galaxy becomes strong enough, it could significantly alter the night sky's appearance. An active nucleus at our galaxy's center would become one of the most brilliant objects visible, creating a new, bright point of light for you to see with the naked eye. This would fundamentally change the celestial landscape and increase the overall background luminescence of the night. During the galactic merger, you can rest assured that direct collisions between star systems and the central black hole will be exceedingly rare. This is due to the almost incomprehensible voids between stars. For instance, the typical distance separating stars in our part of the Milky Way is several light-years. As the two galaxies combine, their stars will mostly drift past one another, making direct impacts exceptionally unlikely. Even though the gravitational turmoil will surely reshape the orbits of countless planetary systems within the new larger galaxy, the actual absorption of a star by the black hole is not a probable event. The likelihood of such an encounter rises in the dense galactic core where stars are packed more tightly, but even there another outcome is far more common. A star is much more likely to be gravitationally flung into a new orbit or ejected from the galaxy altogether than it is to be consumed. Throughout the merging process, powerful gravitational interactions will redistribute angular momentum across the entire system. Tidal forces, for example, can slow the rotation of the galaxies, transferring momentum and allowing some stars and gas clouds to drift into orbits closer to the central black hole. However, for any matter to actually fall in, it must lose a vast amount of kinetic energy in addition to its momentum, which typically occurs through friction within an accretion disk. Therefore, most star systems will either adopt new orbits or be cast out into intergalactic space. The future of the Magellanic Clouds, the two dwarf galaxies that orbit the Milky Way, is uncertain in the context of this merger. Several scenarios are possible. They could be absorbed by our galaxy before Andromeda even arrives, pulled in by gravitational decay over time. Alternatively, if they are still in orbit when the collision begins, they could become part of the larger three-way merger. There is also a chance that the immense gravitational forces will eject them from the system, sending them off to wander the cosmos as independent galaxies. Which of these fates awaits them will depend on numerous factors, such as their current velocity, mass, and the precise details of the interaction between the Milky Way and Andromeda. It is worth noting that collisions and mergers between large galaxies are a fairly normal part of cosmic evolution over immense timescales. In densely populated areas like galaxy clusters, these events happen roughly every few billion years, serving as a primary mechanism for galaxy growth and often igniting spectacular bursts of star formation. Looking at an even larger picture, our local galactic environment is itself being pulled toward the great attractor. This is a significant gravitational anomaly, a vast concentration in the distribution of galaxies that sits approximately 150 to 250 million light-years from Earth, influencing the motion of everything in our cosmic vicinity. A specific area of space appears to be exerting a powerful gravitational pull on the galaxies and galaxy clusters within our cosmic neighborhood, which includes the local group that our own Milky Way is part of. This region, first identified as the Great Attractor, was discovered because numerous nearby galaxies, based on their redshift, seemed to be moving toward it. However, investigating this phenomenon is exceptionally challenging, as it is located within the zone of avoidance, where dense interstellar gas and dust in the Milky Way's plane obscure our view. More recent investigations have revealed that the Great Attractor is not a singular object, but rather an immense cluster of galaxies called the Laniakea supercluster, which also contains our Milky Way and tens of thousands of other galaxies. It is therefore understood not as a single entity, but as a vast region with a high concentration of mass, generating a gravitational field so intense that it shapes the movement of galaxies across the surrounding expanse of space. The accelerated expansion of the universe, a phenomenon driven by dark energy, becomes the dominant force on scales that surpass the gravitational influence between galaxies and their clusters. Within relatively small cosmic distances, such as inside galaxy clusters and superclusters, gravitational attraction prevails, leading to mergers and other interactive events. However, on scales of hundreds of millions of light-years and greater, the universe's accelerated expansion takes over, causing the distances between these massive structures to increase. At these immense distances, dark energy's influence causes galaxies to recede from one another at an ever-increasing speed. Consequently, there isn't a precise boundary where expansion starts to overcome gravity. Instead, it's a gradual transition. As you look at progressively larger scales, the effect of accelerated expansion simply becomes the most significant factor shaping the cosmos. Modern astrophysics is grappling with profound research questions, the answers to which are vital for comprehending the universe's structure. Among the most significant puzzles are the mechanisms behind the formation and growth of supermassive black holes at the centers of galaxies. Scientists are striving to learn how these colossal objects achieved such staggering masses, and to uncover the true nature of their symbiotic relationship with their host galaxies. The process by which black holes feed, known as accretion, is also a subject of intense study, particularly because the inflow of matter is often irregular, producing dramatic events like powerful jets and flares of radiation. Crucial questions remain about how black holes shape star and galaxy formation, their function in redistributing matter and energy throughout interstellar space, and the overall effect they have on the evolution of their galaxies. Furthermore, the scientific community is deeply interested in exploring how dark matter influences black holes and their immediate environments. Astronomers are also dedicated to understanding how black holes interact with other vast structures, such as galaxy clusters and the filaments that make up the cosmic web. The cosmic web itself is composed of immense universal structures, consisting of galaxies and intergalactic gas, held together by the force of gravity. The term filament is derived from the Latin for thread, which aptly describes these long, slender formations in cosmology. These cosmic filaments act like fibers, connecting clusters and superclusters of galaxies to form an intricate network that spans the largest scales of the universe. These filaments, alongside vast, nearly empty regions known as voids, give rise to the complex, web-like pattern that permeates the entire cosmos. The discovery of this grand structure emerged from extensive astronomical surveys and sophisticated computer simulations. The initial clues to its existence appeared in the 1980s from large-scale galaxy mapping, which demonstrated that galaxies were not distributed uniformly throughout space. A detailed visualization and study of these filaments only became achievable with the advent of more advanced telescopes, sensitive detectors, and powerful computer models capable of simulating cosmic dynamics.
Modern three-dimensional maps of galaxy distribution have provided astronomers with definitive confirmation of the cosmic web and have allowed for the detailed examination of its properties. In addition, recent research using methods like the Sunyaev-Zeldovich effect and gravitational lensing has significantly deepened our grasp of this cosmic architecture.
It is widely believed that these filaments originated from minute density fluctuations in the very early universe, which were dramatically amplified during the inflationary period shortly after the Big Bang. These initial variations, reinforced by gravity and composed mainly of dark matter, created the gravitational framework for matter to subsequently condense and form galaxies. Over cosmic time, as matter continued to collapse under its own gravity, galaxies and galaxy clusters started to take shape. At the heart of many of these galaxies, supermassive black holes emerged, exerting a profound influence on their surroundings. As you've seen, these supermassive black holes can actively draw in matter, releasing tremendous energy and sparking processes that create active galactic nuclei. This activity can expel matter into intergalactic space, which in turn alters the properties and distribution of the gas that forms a crucial part of the cosmic web's filaments, demonstrating that these are not static structures but dynamic, evolving components of our universe. This particular interaction is a crucial driver in the development of galaxies, and it may even direct the growth and activity of the supermassive black holes residing at their cores. Our understanding of space is constantly pushing past previous boundaries, a progression largely powered by the creation and deployment of more advanced telescopes like the Extremely Large Telescope and the James Webb Space Telescope. These remarkable instruments enable astronomers to examine objects that are fainter and more remote than ever before, including the filaments of the cosmic web and supermassive black holes, thereby giving us a much clearer picture of the universe's fundamental structure. Among the most profound puzzles we face are the questions surrounding dark matter and dark energy. I believe that deciphering their true nature would completely revolutionize our conception of cosmic evolution. The scientific community is also anticipating major advances in the study of quantum gravity, which holds the promise of unlocking new paradigms for understanding black holes and the very fabric of space-time. At the same time, gravitational waves, which are already being detected by facilities like the Laser Interferometer Gravitational Wave Observatory, or LIGO, and Virgo, will continue to deliver crucial information about the universe's most dramatic events and its overall architecture.
As technology continues to evolve, our computer simulations will gain ever greater accuracy, allowing you to virtually witness and analyze cosmic phenomena that are currently impossible for us to observe directly. While concepts like rapid interstellar voyages or leaping across space are still confined to the realm of science fiction, the dedicated search for new physical principles and innovative technologies never ceases. I often wonder if one day such incredible journeys might become attainable, perhaps unlocked by new insights gained from studying supermassive black holes.
The universe is filled with countless mysteries, and I am certain that each new finding represents another step toward making what seems utterly impossible today a reality for you tomorrow. This journey of discovery continues, and it is a fascinating story of our quest to understand the cosmos. This concludes our exploration of these cosmic frontiers for now, but the pursuit of knowledge never ends. Be sure to stay with us for more deep dives into the universe's most captivating secrets.